Hello everyone, and welcome back to another video lesson. In this video, we're going to discuss common stoichiometry problems and how to approach them, including mass-to-mass problems, mass-to-volume questions, and limiting reactant problems. Let's review stoichiometry problems and how you should approach every problem. Every problem is going to be a little bit different, but with a little bit of critical thinking and a little guide, such as your stoichiometryville map, will help you go a long way. The first thing that we need to remember, and this is a review from the last video, is that a balanced chemical equation represents and conforms to the law of conservation of mass. And without a balanced chemical equation, you cannot do stoichiometry problems. So if a question gives you a sentence describing what happens, you have to convert that to a chemical equation and then balance it. When you balance an equation, remember, you never change the subscript of that particular formula. Water will always be H2O. You can't make it H4O to balance an equation. You only change the subscripts, or the coefficients. When you have a balanced chemical equation, the atoms and the mass of the reactants is equal to that of the atoms and the mass of the products. Nothing is created, nothing is destroyed. It only changes form. We use coefficients in a balanced chemical equation to relate the mole ratio between each substance in that reaction. So remember, the mole ratio is what we use to basically convert what we know of a given substance to what we want to know about another substance. And we're going to look into more of that today. Coefficients are used in constructing this mole ratio. So again, that's why we balance the equation. When we have a chemical equation, the grams of the known must first be converted to moles. So in all these problems, your first step should always be take what value they give you, whether it be mass, volume, or some other particular starting point, and convert it to moles. Once it's in moles, you're then going to use the molar ratio to convert from the known substance to the unknown substance. And then from there, you can then convert to wherever you want to go. In the case of mass-to-mass problems, you would convert to grams. If it was mass to volume, you would convert to volume or to particles or to whatever the question asks. So let's take a look at an example. Let's start off with a mass-to-mass problem. The question says, what is the mass of aluminum oxide, or I'm sorry, what mass of aluminum oxide can be prepared by the reaction of 67.5 grams of aluminum and oxygen? So what's our first step? It's to write that balanced chemical equation. And based on the sentence, this looks like a synthesis reaction. It looks like when we combine aluminum and oxygen, which remember oxygen is diatomic, so it would be O2, we're going to get some amount of aluminum oxide. Remember, aluminum and oxide, when combined, is an ionic compound. So you have to make sure the charges of the aluminum cation is equal to and in the correct ratio with the oxide anion. So let's write down that equation. If we wrote it down correctly, it would be aluminum plus oxygen gas, and that would give us Al2O3. Why is it Al2O3 and not ALO? Remember, aluminum has a charge of 3 plus, oxide has a charge of 2 minus. So we have to make the charges equal, and we do that by adjusting the ratio of aluminums to oxygens. So it should be Al2O3. Once you have your skeleton equation written, next we're going to balance it. You notice that on the right here, I have 2 aluminums and I have 1 aluminum. I have 2 oxygens and I have 3 oxygens. My advice would be to balance the oxygens first. If I look at O2 versus O3, I can never get those the same by just adding O2 to one of them. I have to change both of them. So let's use a common factor of 6. If I have 2 aluminum oxides, that would be 6 oxygens on the right. And if I put a 3 here, that would give me 6 oxygens on the left. Next, let's look at my aluminum. Well, by adding the 2 here earlier, now I have 4 aluminums, and it's very easy to adjust this aluminum because it's monatomic. It's just aluminum by itself. Now we have our balanced equation. Let's jump into the stoichiometry. What do I know, and what am I trying to solve for? I know that I have 67.5 grams of aluminum, so I know I have that much of this stuff here. I want to figure out how much mass of this stuff over here am I going to get. So let's write that down in our equation. I know I have 67.5 grams of aluminum, and I'm trying to figure out this much here. So if you look at your stoichiometry map, I'm going from mass of aluminum to moles of aluminum, moles of aluminum to moles of aluminum oxide from the coefficients here. And then once I'm in moles of aluminum oxide, it's one more final step to give me mass of aluminum oxide. So let's set that up. I know this seems like a lot, but let's digest it piece by piece. I have 67.5 grams of aluminum, which is right here. I'm going to divide that by the molar mass, which you get from your periodic table. You'll find that the molar mass of aluminum is 26.98. Let's round that up to 27 since it's so close. So if I take 67.5 and divide it by 27, I now have my moles of aluminum. And you'll notice that this here and this here cancels out. Now that I know how many moles of aluminum I have, I'm going to use the coefficients from the balanced equation to convert from moles of what I know, which is aluminum, to moles of what I want to figure out, which is my aluminum oxide. So I'm going to divide by 4 moles of aluminum and then multiply by 2 moles of aluminum oxide. Again, where did this 2 and 4 come from? It came from my coefficients here in the reaction. So if I stopped right here, I would know how many moles of aluminum oxide I would get in this reaction. And again, I know this is true because of the law of conservation of mass. What's my final step? Well, the question wants me to figure out what is the mass of this aluminum oxide. Once I know how many moles I have, I can multiply by the molar mass of aluminum oxide to figure that out. Where did this 102 come from? Well, if I look at my periodic table, I find 2 times the mass of aluminum, which is 27, plus 3 times the mass of oxygen, which is 16. You add that up, that gives you 102. So to kind of take a step back and look at a big picture, I'm taking 67.5 divided by 27 times 2 divided by 4 times 102. And when you round that to 3 significant figures, which comes from the question, you find that your mass of aluminum oxide is 128 grams of Al2O3. Try this problem on your own. See what you get. Pause the video and review the answer in a second. Okay, let's go through this. Glucose is used as an energy source by the human body. Calculate the number of grams of oxygen needed to oxidize or burn 12.5 grams of glucose. Write the balanced combustion reaction. Again, we're going to take the same approach as we did before. Your first step is to write a balanced chemical equation. Now, they don't tell you the formula for glucose, but glucose is very common. It's C6H12O6. So if I write this as a balanced equation, it should look something like this. Again, C6H12O6. With every combustion reaction, we know we're going to add oxygen gas to it, and our products are going to be carbon dioxide, or CO2, as well as H2O. Then we have to balance it. I have 6 carbons on the left. I need to put a 6 here in front of CO2 to give me 6 carbons on the right. 12 hydrogens on the left. 6 times 2 would give me 12 hydrogens on the right. On the left, I have 6 oxygens plus some amount here. But if I look at the right, how much do I have? I have 12 from CO2 plus 6 from water. So 12 and 6 would give me 18. So I have 18 oxygen atoms on the right. I already have 6 on the left. So how am I going to adjust this? Well, 18 minus 6 would give me 12. So I need to get 12 oxygens from here. How do I get 12? 6 times 2 would give me 12 there. So now my equation is written out, it's correct, it's balanced. That's the first and most critical step. Now let's identify what I know and what I'm trying to solve for. The question tells me I have 12.5 grams of glucose. So that's this stuff right here. I've got 12.5 grams of this. They want us to calculate the number of grams of oxygen needed. So I'm going from grams of glucose to grams of oxygen. So if you looked at the previous problem, I'm going from grams of glucose to moles of glucose. Then I'm going to use the mole ratio from the question, which is 1 mole of this, glucose here, to 6 moles of oxygen. Once I have 6 moles of oxygen, or once I figure out how many moles of oxygen I have, I'm then going to multiply by the molar mass of oxygen, and that will give me how many grams I have. So let's see that work. Again, I know it seems like a lot all at once, but let's digest it. This should actually be corrected. This should be 12.5. Ignore the 12.3 there. That was a mistype by me. So it's 12.5 grams here, divided by the molar mass, because I want to convert from grams to moles. If you follow your stoichiometry Veil map, grams and grams cancel. So 12.5 divided by 180, that will give me my moles of glucose. Then I'm going to use the mole ratio. So 1 mole of this to 6 moles of this. So I have 1 mole of glucose, which cancels out with moles of glucose here, 6 moles of O2 here. Last but not least, I have to figure out the mass. For every 1 mole of O2, I know from the periodic table that 2 times the mass of oxygen, which is 16, would give me 32 grams of oxygen here. So in conclusion, I'm doing 12.3 divided by 180 times 6 times 32. And my answer here should be 13.3 grams of oxygen. Thank you.